All right, so I'm talking about section 1.6, other types of equations, and we're dealing with the radicals at this point. So when you have a radical in your equation, your method is to isolate the radical to one side, and then if it's a square root, you're going to square both sides to move forward. But this example we're going to start with is a cube root. It's example 6. You have a cube root and another cube root. If I throw this cube root to the right side, I'm going to have isolated this first radical term, and again, throwing the radical across the equal sign will change its coefficient sign to a positive over here. It's still the same old radical though. So these are both cube roots, so if I would cube both sides, I'm allowed to do that, it's going to just make those radicals cancel out for me, and then I'll have a much easier equation to deal with. Just remember, when you use this trick, sometimes you get extra solutions, so you always have to check to see which ones really work. So the radicals are gone now, so release that radicand stuff out from under the radicals, and we've got a quadratic equation. So we're probably getting kind of used to me saying that. Here's another quadratic. Solve it by getting it all to one side in standard form. Standard form is in order and equal to 0. Once it's in standard form, that's your A, B, and C if you prefer to use the formula to solve it. I'm usually going to factor these. Just kind of know that. That's up to you. I'm kind of guessing 4 times 1, but it might be 2 and 2. But I feel like maybe I can see how this would give me a 5, and it does. If you check all that out, FOIL it, that foils to give me a negative 5 in the middle. So that is okay. Then I set each part equal to 0, giving me 2 potential solutions of 1/4 and positive 1, which both have to be checked. So we'll plug them in one at a time. In the original problem, make sure that they balance it out and work. And to save a little time, you can just see it in the book, but they do check that both of these work this time. So there's 2 solutions, both of the proposed solutions work. Okay, let's do another. Let's go back to example 5. It has 2 radicals and a constant. So in this scenario, there's no way to truly isolate your radicals one to each side because we've got this extra term that's going to make that impossible. There's 3 parts to this. So yes, I can throw that across the line, and I do want to start there, but it will isolate this radical, but then this radical will join with a +1, and that number doesn't need to be there. It's a real value constant term. So sometimes, you know, we don't worry about 1. If it's multiplied in front of something, it's not a critical one. But if it's just a constant, there's a 1 there. Yeah, you got to have it. It's a powerful extra term. So this radical is no longer isolated. So it does cause us a little bit more trouble. So we can square this radical, and that's great. Cancel out that radical and bring out the 2x plus 3. But it creates sort of a mess on this side, because when you square the side, which is what you have to do, the same thing to each full side, when you were multiplying, multiplication distributed, and that was all good and fine. But with squaring, it does not distribute. You can't just say square that, not distributive. So what it is actually a binomial squared. You can use the binomial squaring pattern, or I'm going to illustrate it by actually showing you when you square this, that means that times itself, which would be the FOIL method. So when we FOIL this side, here's our first and first. So you've got a square root of x plus 1 times the square root of x plus 1. When you times something by itself, it's like squaring that square root. It will just bring out the x plus 1. The outer is 1 times x plus 1, or just x plus 1. The inner is 1 of that as well. And last times last is a constant 1. On the left side, nothing to do there, just bring that down. Then combine any like terms that you can. I see I've got an x. I do see I've got a 1 and a 1. That can be combined to be 2. And then these would be considered like terms. They're like radicals. So 1 of this radical, 1 of the same radical makes 2 of that radical. So we're making some progress. Although you might note, yes, there's still a radical in it, so we have not got rid of the radicals completely. So now we go through and we isolate that radical and we do the squaring process again. So it makes us have to go through the process twice when you have this set up. So I'm isolating that, so I'm throwing the 2 across, I'm throwing the x across, 2x minus x, 3 minus 2, leaving me 2 radical x plus 1. At that point, if 2 would divide and not cause me fractions, I would divide even out the 2, but it will make a fraction, so I probably wouldn't go that route, but we're making progress. We've got it down to just these 3 terms. At that point, I will square each side again, since I have the radical term is isolated. When I square this, it's not a binomial, right? The 2 is times onto that, so there's really just one term there. So you square the 2 and it's 4, and when you square the square root, it's x plus 1 brought out. So this becomes 4x plus 1. This side, there's a binomial again, binomial squared, so we times that by itself, or use the squaring pattern. That's showing up a lot here, but first, outer, inner combined, and last. At least the radical is gone now, and we come up with a quadratic again. Distributing the other side, we have a quadratic equation. Let me see if I can bring this up here. Maybe we can see it better. These problems are just long problems. We got to bring the 4x across, get it in standard form. But when you, let's see, let me show you that step. Here's what we've got so far after squaring both sides again. Then it's a quadratic. The x squared means bring it all to one side, get it in standard form. So when I'm minus 4x, that's negative 2x left. And when I'm minus 4, 1 minus 4, you've got this quadratic equation in standard form again. From there, it's that factoring or using the formula. And you know I like to factor it. Set each part equal to 0, giving me 2 potential solutions of 3 and negative 1. Again, they're potential solutions. With the radicals, you could have compromised the sign even though you worked so hard for that. You've got to go back up and check it. So let's do that. Back in the original problem, you know, you've got to plug in these answers one at a time. And I know you're like, you've got to be kidding me. This is the longest problem. And I agree. I am always as happy as anyone to get through a section 1.6, and 1.7 is still sort of like that, and then I think it gets much easier. So hang in there if you're like, oh my gosh, she's driving me crazy. Just keep on keeping on, and I think the material gets a little easier after chapter 1, if that's some good news for you. So there's square root of 9. It would be square root of 9 is 3, square root of 4 is 2. That one actually works out just lovely. So that solution, good. Then we go through the process again, checking our answer of negative 1. So we plug negative 1 back in. Okay, so same thing. Plugging it in for each of these x's, seeing if negative 1 solves this problem. 2 times negative 1 is negative 2 plus 3. You can use your calculator all you like. Negative 1 and 1 is 0. Well, I think that's going to work as well. 1 minus 0 is 1. That is also true. So both of our solutions worked out. There's really no pattern to it. You just have to check it if you're kind of thinking, can you just tell me, does it usually do this or that? And I can't. You just have to check them. All right, so radicals. You isolate the radical one at a time, square or cube, whatever the root is, and then move from there. Sometimes the process has to be done twice, and then you have to check your answers. All right, one more thing before we move to the last type of equation that's sort of related to radical is example 7. We have a fraction exponent, like so. So the concept of do the same thing to each side is what we do in algebra. So we're going to use whatever trick helps us get the x solved for. So here we have an x raised to a 3/5 power. And again, this is example 7a. So because it's raised to the 3/5 power, again, my goal is to get x to the first. So if I raise this to its reciprocal, 5/3 power, exponents to exponents multiplies the rule. So 3/5 times 5/3 makes just 1. Since I picked its reciprocal, it all cancels. That is x to the first, or regular x that we always try to solve for. Whatever you do to one side, you do to the other side. So when I take the other side, 27, raise it to the 5/3. That's something to do on your calculator, and I'll tell you to practice that. Always practice with your calculator as we go. But that one does come out nicely. It's this 5/3 power, which again, you can just totally do it on your calculator, but by hand, the denominator tells you what root this is. This is a cube root, and 27 just happens to be a perfect cube root. So the cube root of 27 is 3. Then you'd raise it to the 5th power. So 3 raised to the 5th power. We'll have to look for that one to tell you for sure, and that is 243. But you can totally practice that on your calculator and jump right to the answer, 243. All right, one more like that. Example B part. So here we have a quantity to the 2/3 power. So same trick I just used. If it's to the 2/3 power, I'm going to take to the 3/2 power. Now the reason this is sort of related to radicals is, I don't know if we've talked about it this class so far, but radicals are the same thing as fractional exponents. It's just a different way of expressing them. Like to the square root means the 1/2 power. So they are related. We could write this as a radical as well. But this is kind of nice, you know, taking the power to its reciprocal is a nice way to work these. Cancels that out, brings out the base there. Do the same thing to this side. Raise 16 to the 3/2 power. Again, I'm having to look because I didn't have that memorized just the moment, and it's 64. And it's actually plus and minus 64 because you've used the square root property on this, which means you have to say the plus and the minus answer, just a little kind of extra detail there. There are 2 potential solutions there. Because of that, whenever you take the square root of each side, and by doing the 3/2 power, that is a square root, so there's a plus and a minus of that. So you get 2 answers. X minus 4 is 64. X minus 4 is negative 64. Solving to give us 68 is one solution, and plus 4 on this one is negative 60. Now we should always check. They do show that checked on each one of these, and both of those answers do check out. The negative 60, and I know you're like, oh my gosh, I can't believe I have to do all that, but that is the only way you know for sure if you got the right answer. You've invested so much work to get even there. You've got to check them back in the original problem, make sure both do work out, and they do. So 68, negative 60 is the solution set in no particular order.